All right, and welcome to the third week of Wireless Cellular Communications. Today we have a pretty big lecture, so I'll try to make room for questions for homework at the end, but if not, we'll do it the next time, and we'll go over homework number 1, 2 if needs be. So let's keep that for the end or the break, and we'll talk about that. Otherwise, I want to talk today about propagation and various related subjects, which is, of course, very important to any wireless system. So we'll talk about propagation. I'm sure you've all seen that little curve there that has something that vary greatly over a small amount of distance or sometimes time. This represents the power received divided by the power transmit as you drive away, from instance, from the transmitter. And the way to model this little curve that seems fairly random is a classic three-way modeling, if you will. The first one is the path loss, a very simple rule as a function of distance. The second one is shadowing, usually log normal. And the third one is to account for the very small fades, which are represented like that. So that overall green curve will really be decomposed over 3 different models that we'll talk about this week. The first one, maybe the small scale variation, is probably the easiest one to get rid of. Remember, we talked about spatial diversity. When you have a few antennas, a few lambdas apart, you'll get rid of the little fast fades that, or small scale fade that happen over small distances. So when you measure things driving away from the transmitter and you have something like that green curve, how do you eliminate that fading? If you try to model more than just those deep fades, usually you average those over a number of wavelengths, and then you get something like the red curve. How do you measure the shadowing effect? Well, you usually do a regression model, and you try to get that blue curve. You subtract that, and you have sort of that zero mean shadowing, and that's the sort of thing we're going to talk about this week and next. We'll talk about some very simple models, what happens in free space when there's nothing around. Of course, there's usually something around, at least the ground, and so we'll see what happens when electromagnetic waves reflect off the ground, diffract off buildings, scatter off various elements. And we'll talk about a few models that have been popular to model all this. Have you all, before I go too much into detail, I can really fly over that fairly quickly, or I can go, to spend more time on some of the models, or I can go slower if you haven't seen any of those models. Have you all seen Freeze equations and basics of propagation modeling, maybe in wireless systems? Okay, so I'll go fairly quick over some of that, and stop me if you have any questions. Well, that's a pretty pale picture to show antenna gain. I'm not sure you can see much. Maybe I can, yeah, of course, my pen loses its calibration every time. I'm not sure if you see that, but there's really 2 circles here, and just 1 big circle here. This is the antenna pattern of what? Anyone recognizes this? The one at the bottom? Dipole. Very good. A dipole that's basically vertical here, and that's fed, by 2 wires, and basically the signal feeds that dipole, and that dipole doesn't transmit anything up or down. So if it's a vertical dipole, its beam width is in the azimuth plane. It's of course in all directions, same gain, which is why there's that circle here. That's the azimuth. And in elevation, its main beam is at elevation angle 0, but it doesn't transmit anything at elevation angle 90 degrees. Often we need that in 3 dimension, so that basically at any point when you feed an antenna here, it's got gain, a certain gain in any direction. We often talk about the maximum gain of the antenna. It's in its bore site, and but keep in mind that gain varies with angle of azimuth and elevation. So the antenna gain is what defines, who knows the definition of the antenna gain? The antenna gain is the, yep.
Power that you receive per unit area.
No, the antenna gain is a gain in a certain direction with respect to an ideally isotropic antenna. So for instance, if you had an antenna, and such antenna doesn't exist, we can't make one that transmits ideally isotropically, and then you make another antenna, well, it has a certain gain in a different direction. In the bore site, usually the gain is greater than 0 dB, because you want it, or dBi for isotropic. And outside of the bore site, say in the back lobes or in the nulls, it's much less than 0 dBi. And the dBi is what refers to the gain of the antenna with respect to an isotropic antenna. Sometimes you'll hear dBd too, which is with respect to a dipole, which is the one drawn down there. So instead of a dBi, you can have an antenna gain in dBd. The I of dBi stands for isotropic. The I of dBd stands for dipole. And the dipole has a gain in that direction of its bore site. Anybody remember the gain of a dipole? 2.18 or 2.17. I forgot exactly, but I forgot the exact number. It rounds to 2.17 dBi. So basically 0 dBd equals 2.17 dBi. So manufacturers like to give the gain in dBi because it looks bigger, it sells better than a gain in dBd. Because if I want to sell you an antenna at 17 dBi or another one at 15 dBd, they're the same, but the one at 17 dBi sounds better. So, plus, silly to compare to dipole. Comparing to isotropic makes sense. It's just some people didn't like to do that because an isotropic antenna doesn't exist, so they wanted to compare it to something that exists, but never mind. The other aspect of importance on the receive side is the effective aperture area, or the effective area of an antenna. And that's the area that it effectively captures the signal. And that's related to the gain. We'll see how. It's not quite obvious. The free space model, you can see the derivation of that on that slide or in the class note in section 3.2, is a fairly simple spherical growth of the wave argument. And let me just go over the main point. I'm sure you've all seen that demonstration, right? So the main point is that you have a certain amount of power transmitted here. Yeah, I forgot to put a pen, of course. And I'm not sure I can. So you have a certain amount of power transmitted here, and if you transmit it isotropically, it makes sense that that power stays constant within a sphere, right, by the conservation of power argument. And how much power do you receive at a certain area at a distance d from that transmit point? So this is transmit point T, this is R. Well, you receive the transmitted power times the gain of the antenna that transmit that power in that direction times that fraction of the power that intercepts that area. So that the ratio of that surface divided by the surface of the entire sphere, right? Because the power is conserved, but the one you can only receive is a certain portion, the one that your antenna sees. So it's the ratio A sub B of the received side divided by 4 pi d squared, the whole surface of the sphere at distance d. The next little trick is this fundamental definition of, well, actually the definition is that one. The definition of the effective area is, it's by definition the gain times lambda squared over 4 pi. And that definition comes from the fact that an area relates to lambda square as the gain of the antenna relates to a 4 pi solid angle. Have you heard of solid angles? It's angled in space. Instead of a 2 pi total of the circle, you have a 4 pi solid angle total in the omnidirectional view. So that's why it's defined that this effective area is the gain lambda squared over 4 pi. If you plug that in there, solve for AE, you get that little expression, P received equal P transmitted times the gain of the transmit antenna times the gain of the receive antenna times lambda squared over 4 pi d, everything squared. Then we change lambda equals C over F. We move PT on the other side of the equation, and we get something that the power received over power transmitted equals the product of the gains times the inverse of the path loss, right? If it's the inverse is just because the loss, it's defined as a loss, therefore the power transmitted divided by the received power is the loss, but the power received divided by power transmitted is 1 over the loss. And so that loss, path loss, L of D, is 4 pi squared over C squared, F squared, D squared. Usually that's put in dBs. But we have to be very careful. You can't just take 20 log of that dB because, well, actually, you can, but you have to be careful as you start isolating things like let me see. That's a constant, right? What's the dimension of FD? Has no dimension, right? F is a frequency, D is a distance. Together, multiply, they have no dimension. So you could take the logarithm of that. But we like to separate the frequency and the distance. So to separate that, if you just take 20 log F plus 20 log d, in other words, the path loss in dB, so 10 times the log of that L of d, is a certain constant plus 20 log f plus 20 log d. But you have to be very careful that that constant depends on what unit you use for f and d. So you can do that several ways. Very often you'll see that formula that you can barely see at the bottom because of that. There, I removed it. You'll see something like that the path loss is 32.44 times 20 log f times 20 log d. But that constant 32.44, when you see it, right away you'll know that it means f is in megahertz and d is in kilometers. Or equivalently, f is in gigahertz and d is in meters. But you have to be very careful. Some books are not too careful how they derive that. So the best way to remember that is that constant depends on a dummy frequency and distance of reference, f0, d0, that are then, what I did here, basically you multiply by and divide by f0. So the numerator has an extra f0 square, so the denominator have it. That's why you see that the constants come here into that constant, and the f over f0, d over d0. Sometimes you'll just see 20 log of f in megahertz plus 20 log of d in kilometers. It's the same, which is fine, but be very careful when you manipulate those. Sometimes you change things and you use the path loss. Remember the units associated with the things inside a logarithm. So simple, obvious math, but sometimes if you forget it, there can be mistakes in linked budgets. You can have a factor 1,000 that appears here or there, or 30 dB that start appearing here or there, and that can be embarrassing. Any question on that? Probably spend too much time on that slide. Next, we're going to see a little bit about ray tracing. And that's the only part of the course where we're going to spend a little bit of time in notations. And we have to be a little careful because to look at the ray tracing, we need to pay close attention to what the signal looked like. And I'll invite you to read carefully those definitions in the course notes, section 3.1. If you have any questions, ask me. Ask me way before the homework is due, because you'll need to use that for homework. Although you can probably complete the homework without understanding it fully, but make sure you spend some time reading that and understand. So what we're really doing, normally we just consider the power, and we're, engineers just have an overall measurement of the power and claim that's usually good enough for what they're trying to get to. We'll see for MIMO, it's not quite true. We'll need to be a little more careful about what the signal path and the various layers are. And this is a little bit like that. Ray tracing, you'll see, is in a way a bit like MIMO. What we're doing here is we have to define what we're transmitting. And we're assuming we're identifying the electric field with our signal. In other words, we're transmitting something, a signal, S of t, which is a little s of t, like look at that one as a symbol transmitted, every fraction of a second, times the complex exponential j2 pi ft, where f is the frequency of the carrier, t is in time. The signal really is the real part of that, but it's easier to represent it in complex form. And then the real part is s cosine 2 pi ft. And on the receiver end, we're going to receive r of t cosine 2 pi f of t, which is the complex exponential r exp j 2 pi ft. And of course, between S and R, there's going to be a bunch of attenuation problems, etc. We could make things a little more complicated but more realistic by saying, really, we transmit usually two signals at the same time, right? A cosine and a sine. But for now, let's just say we just transmit a cosine. Everything else happens the same. We can expand on that later. But we transmit it on the electric field. Why is that important? Because things are going to bounce off things with a ray, and we're going to try to see how it bounces off surfaces. And it's easier if you just consider the electric field. What about the magnetic field? Are we ignoring it? Not really, but we'll make things very simple, and we'll say that in the vacuum, or by extension in air, I'm not sure if I can circle things again. Things are pretty simple because the magnetic field H is simply at least its modulus is simply related by, and I'm not sure why the letters here disappeared. Let's see, there should be an E here. Well, the ratio of the modulus is simply eta 0, or sometimes Z0, which in vacuum or in air is 377 ohm. So, in other words, the power density, the spatial power density, is given by the Poynting vector, which is the curl product E and H. In this case, when H is just E over eta 0, the modulus of the Poynting vector is just the modulus of E squared over eta 0. Does that make sense? The Poynting vector gives you the power density, spatial density at a given point. And so all we're going to do is study the electrical field, how it propagates, how it bounces off. And whenever we need the power receive, we'll just use that little trick that the power density is modulus of E squared over eta 0. So if we know E at any times, you basically ignore its phase, square it, divide by eta 0, and you know the power density. Now that's just the power density. And remember that little trick with the effective area. How much power do you actually get on a certain antenna? Well, you get the power density times the surface of the antenna. Well, that's really how big is the antenna? What exactly is the effective aperture of the antenna? Roughly think of it as an order of magnitude is the surface of the antenna. But what's the surface of a dipole, right? It's pretty tiny or infinitely thin. There are formulas that give you the effective aperture of, the effective area of any type of antenna. Helix, dipoles, series of dipoles. But if you think of a large antenna with multiple elements, say microstrip designed, or just patches, the effective area of the antenna is usually pretty close to the actual area of the antenna. If you want more details, there's a few references in a class note. Some are a little larger, some are a little smaller than the actual size of the antenna, but give or take a 10% there in the general area. So the power receive is the effective area times that modulus of that electric field received divided by eta 0. We'll only use that in ray tracing. After that, you can forget about all these notations. Well, not really. You should remember them, but ray tracing is very simple. We don't really exactly know how things propagate from transmitter to receiver, so we're just going to use optical rays and say, RF is actually not far from optics. So if you have a transmitter, say on this base station here, and a receiver on a mobile here, what happens is at least there's one ray from the transmit to the receive. Say it's at a distance d0, transmit from receive at a distance d0. The actual distance from the transmit to receive is L0. Can you all see those? It's a little small, but this is d0, the distance, the horizontal distance. This is L0, the actual distance between transmit and receive. And of course, how do you calculate L0? Very simple Pythagorean theorem, right? L0 square equal D0 square plus this little distance square. And what's that? The height of the base minus the height of the mobile. So that's what happens if you ignore everything but that one ray. If you do plot that, you get the so-called one-slope model. If you plot the power received divided by the power transmitted, and you see it decays in 1 over d squared. And here we've plotted, I'm sure this is no secret, you notice that the x-axis is in logarithmic scale. Therefore, when you plot something, a 1 over d squared variation on the logarithmic scale, you see a slope of n equals, I heard somebody say 20. Yeah, I mean the slope is -2 or minus 20 decibel per decade. The second ray is the one that bounces off the ground. Let's call that distance L prime 0. How do you calculate L prime 0? Well, the easiest way is to see that this distance here is the same as the one right bouncing off here. So now again we have a Pythagorean theorem where L0 prime equals, well, squared equal D0 square plus, now it's this distance square, which is simply the sum of the height instead of the difference, right? So same thing, you can calculate that. And all right, the answer is already there, but before I get there, we need to see what happens here. What happens here when the things bounce off the floor? So think about an antenna high up there that transmits something to a handset at someone's ear. There's a direct ray and one that bounces off the floor. What happens when it bounces off the floor? Well, it depends on the polarization of the wave. I'm sure it's nothing new here, but there's darn pen. There is a boundary value problem here, and you can assume that the ground is perfectly conducting. You can assume a number of things, and for now, let's assume that it's perfectly conducting. When it's perfectly conducting, there's no currents created. Therefore, the sum of all the electric field has to be, remember that from undergrad, what happens in a perfectly conducting reflection? The sum of all the electric vectors on the conductor have to be 0. And that, let's assume, for instance, here, that's the equivalent of saying gamma equals -1. The -1 or +1 depends on the various conventions you might use, but with the normal convention that, let's say, if you have the incident field up and the reflected field up, a perfect conductor is a gamma of -1. Same thing here. You can assume, the incident electric field coming out and the the reflected one also coming out. Some will take the opposite convention and have it go in a different direction, and that may change the sign of your coefficient, but doesn't really matter too much. What really happens, though, is that reflection coefficient is not exactly 1 or -1. It depends on a number of things, including the angle of incidence, theta, and, of course, the type of ground. Really a couple of parameters of the ground. Mostly it's epsilon r, the relative permittivity, and its conductivity as well, which in that model is included in epsilon r. So given a different epsilon r, you can ignore usually the conductivity sigma. Sigma here is not a normal standard deviation like we'll see in most of the rest of the class. Sigma here is the conductivity in Siemens per meter, or in 1/ohm per meter. But it's generally not very significant unless you talk over seawater. If you deal with communication over water, it becomes important. Otherwise, you'll see in homework, you'll have to do different things. If you vary epsilon r from those various things, the general picture will not change that much. But anyway, what happens is there's usually a little bit of attenuation, so you lose a little bit of the module, and there's a little bit of phase shift, so things change a little bit, so that when the two waves arrive at the mobile here, and remember they're cosines or complex exponential, when they arrive now with a slightly different distance, and therefore sometimes they're in phase, sometimes they're out of phase, and you'll have to do that in your homework. You have two different expressions, you add them together and plot them as a logarithm of distance, and you'll see those deep fades, and you'll see maxima. The maxima tend to be 3 dB above, right? Because if they add coherently, let's assume there's no loss here, and the distance L0 and L0 prime are similar, the adding coherently is almost taking twice the signal, so it's 3 dB higher. But when they cancel in opposite of phase, again, if you assume that there's no loss and the distance are more or less the same, they can be almost the same signal that in opposite of phase. That means it goes almost to 0, which means that those fades can nearly go to negative infinity. Practically, they can be very deep, 20, 30 dB. And that's what you'll see. The other noteworthy thing is the 1/d squared versus 1/d4. It is sometimes considered that the envelope here minus, if you ignore the deep fade or you'll try to get rid of them with diversity, this slope is 1/d squared. But after a certain critical distance, which is given here, depends on the height of the base and the antenna and the frequency of your signal or wavelength. After that critical distance, the model is in 1/d4. That's significant. That's a much worse propagation than 1/d squared. So even though we have a lot of fade here, when we're in this zones, things are going fairly well considering. I mean, there's lots of deep fades. Some are, significant. But with the nice schemes like diversity, you can probably get rid of them. But after that, it's 1/d4, which is pretty bad if you want a big coverage. In some cases, it's good, though. Why is it good?
No interference to the other channel.
No interference. So there were some very smart attempts at saying, you know what, we want to design cell sites to be just about that critical distance. You see why? So I have ideal coverage within my cell, and then worse coverage on the adjacent cell, and so I don't cause too much interference. And so if you think about it, if you buy a block of spectrum at an auction, right, lambda is fixed. The height of the mobile is fixed, right? It's usually 1.5 to 1.7 meters, right? It can't vary too much. You can't. You have little control, but you do have control over one parameter, the height of the base station. So practically it's pretty high, and well, you can play with that, the size of the base, the size of the cell versus the height of the base station. Practically there's so many other things coming in the play of your design, right? The capacity, coverage, I mean, there's many things you can do, but this is something to keep in mind. Practically, that distance is pretty large compared to, most modern designs where the cell site is something in that range, much smaller than that. But still, if that's the case, just bring the antenna, the base antenna, shorter, lower and lower, which is what happens a lot lately for small cells. So keep that in mind if you can design things indoor, outdoor with that in mind. You won't be able to sometimes. We've talked ground reflection. And then you'll talk about 6 rays and more, even 10 rays. Why do you find so many rays? Well, 2 rays obvious, right? There's always the ground. And then you can start thinking of other buildings around, right? In this simple example, consider R0 from the transmitter here to the receiver here. R0 really hides 2 rays, right? The direct one and the one that bounces off the ground. But you can't see it because this is the view from above. So now consider R1 bouncing off a near building from the transmit to the receiver. Again, there's 2 rays hidden behind R1. The one that you see here, transmit to building to receive, and the one that you don't see, maybe it hits the ground here or maybe here, but it's perfectly vertical with that one. And so that would be a 4-ray model. If you consider one building, you should probably also consider the other one. So there's R2 that bounces off another building. So think of that as a urban corridor. You go down the street, and if you consider R0, R1, and R2, how many rays do you have? 6. And that's the blue line here. I'm not sure if you can still see the red line. It was the one we saw on the previous slide, right? It's got deep fade until the critical distance, then it's one of R4. Now the blue line you see is a lot more erratic and has more things, and then you can, well, it's hard to see, but there's basically more coherence addition. Sometimes it's higher, up to 6, 9 dB higher, or more fades because of non-coherent signal additions. And finally, the 10 rays has even more. And what do I do to obtain 10 rays? I had 6 with 1 circle in red there. And to get 4 more, I now consider bouncing off building number 1 first, then building number 2, then getting there, or building number 2 first, then building number 1, then getting to the receive point. Remember, each one is 2 rays, so that's 4 more. That's a 10-ray model. That starts to look fairly good. Although if you look, it's hard to see, but if you try to see the difference between blue and black, there's not that many difference. So you can only get so much accuracy by adding rays. After a while, I've seen some multiple ray estimations. The more you add, it gets a little better, but the uncertainty due to the model of your terrain become more important than adding rays. We'll get to that, especially indoor. We'll talk about that at the end of today. Yep.
The single slope line.
Yes.
Line here, is it fit to the 2-ray model, or does it fit for all the models?
That's just a 1-ray model. So, good point. It's not a linear regression fit to any of those models. No. Yep. Good question. You could try to find a linear fit to all those models, and the slope may not quite always be 2, right? It can be a little more, a little less, depending on number of things, including your coefficient of reflection, the width of the street, maybe, all sorts of things. Yep.
Is there any practical change in the critical distance with increasing number of rays?
I don't know how to answer that. That critical distance is really only defined for 2-ray model. Oops, I shouldn't have. It's right there. Right, you see that the last hop of that of the 2-ray model. We know that after that distance, there will never be a deep fade anymore. But on multiple ray, there's many fades, and we usually use the same critical distance to say that on average, the envelope is 1 over d squared, then 1 over d4. But an ancillary question is there always a critical distance after which there's no more deep fade? Good question. You can push those graphs, take them to as far as you want, and you can see if there is a critical distance for each one. There might very well be. Yes.
Each ray acts individually, right? Each ray acts individually. So I don't think even the number of rays, propagation strength of the signal will only be indicated with the distance, the number of rays. How many? Let me the no number of rays. Each ray will be acting differently based on the number of reflections and the number of distance. How much distance is going. So I don't think.
Right.
With the number of rays, it doesn't affect the. Each ray will not affect the other.
Each ray very much affects the fades.
If you increase it to 100 rays, each ray has its own property with its distance and the number of reflections and how it produces the power of it.
Sure, but what causes the fades is when the addition of those can be just in opposition of phase, and you never know what ray will just be in opposition of phase at a certain distance. So it could very well be that there's a critical distance after, I don't know, 10,000, 100,000 meters here where they all, none of them can have.
If you sum them up, you'll get a final graph. If you sum all the ray power levels.
That's what this does, yes.
This is the each individual ray. No.
No.
Okay.
This is the sum of all the rays. If you sum them all. If you don't sum up, they all look like the green line. A little off because the distance are a little different, but not much. But it's by summing them that you get that in phase, out of phase, that you get those deep fades. Yep. The only other thing I want to mention is how to calculate those. It's explained in the notes a little better, but this is using Pythagorean theorem in space now, right? Think again what we did earlier for R0. In the vertical plane between Tx and Rx there, we use Pythagorean theorem to calculate L0 and L0 prime. Now we have R1, so we use that theorem in the horizontal plane to calculate the distance for R1, but we still need to do it in the vertical plane for the one that bounces off the floor, right? So it gets a little more complicated, but not that much. I mean, it's just square roots of sums of squares of distances. Does that make sense? In other words, R1 really hides 2 rays, an R1, let's say a distance L1 and a distance L1 prime. The distance L1 is simply if you assume that the transmitter is WT away from the building, the distance L1 is simply the distance D0 squared plus 2WT squared, right? That gives you the, because again there's that that triangle here. So that distance, that triangle gives you the distance L1. And the distance L1 prime is hidden under there. It bounces off the floor, so it's again the same argument given the height of the mobile and height of the base. Right? It's a little complicated, but once you picture it, it's easy to get. And all the formulas are in the class notes if you need to retrieve them. Okay, any questions on ray tracing? That's why I asked you to get some program like MATLAB or something to really get to that, because it gets a little complicated manipulating complex exponential, adding them in and out of phase, and you'll have to play with the how many spaces apart, because sometimes you may miss one of those fade, right? If your plot is not accurate enough, it'll look a little funny and you'll miss some fades. Towards the higher distances, you usually don't miss them, but to the lower distance, be careful not to miss any fade. If it looks too funny, like more like a zigzag or a sine wave that doesn't have fades, look at your interval of points. You probably don't have a good enough sampling method. Other than that, we'll forget ray tracing and we'll focus more on other classic models, and they're reviewed in the order pretty much in the class notes if you want more details, as well as in many books in the area. The COS231 Hata model is very important and still very widely used, so we'll spend a little bit of time on that one. It's really a combination of two models and then an extension of those two models. It combines the Okumura model and Hata model. Okumura came up with the original model in a paper published in 1968 that he measured in Tokyo, and he measured most of those, oh, I forgot his frequency of measurement, but they were in the low end. I want to say 300 megahertz. I'll have to check exactly. And he considered that most of them were valid from in the decade around that 150. Maybe he measured most of them around 150, and he assumed he considered they were valid for about a decade of frequency, and after that we couldn't use his model. So valid from 150 megahertz to 1500 megahertz, which happened to be perfect for the early cellular models around 800 megahertz of spectrum. It was at a time where, computing power was not the greatest, so there were paper curves, and you would just measure things and look at the curves and define the model from there. Hata then later, in 1980, put those curves in formulas. It's really the same model, except now there were very convenient formulas approximating those curves. And then it was modified a little later to go up to 2 gigahertz because, well, PCS frequencies were above 1500. For a while, of course, they just used it at 1500. And then they extended it and changed a few parameters to do that. Then COST, the European initiative to look at all those models, produced a final report. And Chapter 4 is a great read, by the way. Look it up you can find it online for free. Read it. Chapter 4 is a beautiful explanation of anything that can happen in terms of fading, modeling of propagation. I'd highly recommend it if you have nothing else to read one night. And that final report uses that, and that became the COS231 Hata model that really combines all that into one fairly simple to use model. what exactly is that model? Well, it's pretty simply a model for the path loss, L, which is a constant plus a bunch of other terms that represent the variation due to frequency, due to height of the base station, due to height of the mobile. And that's pretty much it. Oh, and there's one other little things that reflects what they call the morphology, if it's urban, suburban, or rural. You've noticed that I kept my sort of promise of putting things in. It's to me easier to write things like that, but sometimes you'll just see F sub megahertz. You just know you have to plug in F in megahertz. The heights of the base and mobile are in meters. And the other constants, C0, CF, A, B, and C sub M, depend on a number of things. The frequency, remember they put two models together, the Okumura-Hata model and then the extended Hata model. The two are meshed together. Well, not really. They're meshed together with two different constants, so they're really still two different models. But now it's called the cos231 Hata model, and the constants vary depending if you're in the old Hata range or in the new extended Hata range. The interesting thing to look at as well is they've restricted the range of the antennas. So this is really only valid for base station heights of 30 to 200 meters. And 30 meters is high. It's 190 feet high. You know, the small cells lately and the smaller modern cells are lower than 190 feet or so. And so we should question whether the Hata model works for small cells and things in 4G, 5G. Same with the cell range. It really works well at long distances, 1 to 20 kilometers. You know, nobody has cells 20 kilometers anymore. Well, maybe in rural areas, in some areas. But if the distance, the range of your cell is less than 1 kilometer, which it often is lately, start questioning the Hata model. Some say you should not use it, right? This defines a domain of validity. Practically, you can always use it, see what happens, compare it to your data. It may or may not work too well. And then A and C are a very small change. C is just plus or minus plus 0, plus 3 dB, depending on the size of the city. And A varies a little bit with the height of the mobile, but really not much. The interesting part to look at is this. The factor in front of the log D. That gives you the slope or the path loss exponent. You'll notice that that path loss exponent decreases with what? The height of the base station. So the higher the base station, the lower your path loss exponent. The lower your base station, the steeper the path loss exponent, right? The propagation is not as good with a lower base station. Seems obvious, but it's sometimes very useful to just use that as a base of reference for any measurement you may make. Any question on Hata model, cos231 Hata? Yes?
So, how do they come up with this equation?
Excellent question. Again, by putting together various models. But basically the start of it was that the path loss exponent times the log of the distance, right? They took a whole bunch of measurements, originally in Tokyo, and they said, you know what, that looks like a linear regression fits well if the distance is on the logarithmic scale. Linear regression fits well, and the slope are a little different depending on the height of the base station. Therefore, we're going to have something with the height of the base station times log of the distance. And then all the other things, well, that one was failed. Remember in free space we had a 20 log f, so that C sub f is something that's going to be pretty close to 20. And, well, in the original Hata model it's 26, and in the other it's quite big. And that's been criticized, that's a little too big. We expect things to vary in 20 log f. And why did they get there? How did they get there? Measurements, tons of measurements, and then linear regression.
So they kind of did they just beat around the bush and find an equation? Is that how it is?
Yes, they basically said, well, we know it varies with f. How does it vary with f? Go out there, do measurement campaigns. And they measured everywhere. And we'll see in the ERSEG model, same thing. There was AT&T cell sites everywhere that were measured, put all that data together and derived those numbers. How? When you don't know linear regressions. It's really that simple. You have a question? Or?
What did they measure exactly? Like, because in the first model came up in 1968, right? So in 1968, there was not a lot of activity when it came to cellular. So.
Oh, yes. That was all Okumura's measurements. It was continuous wave throughout the city of Tokyo. They had a transmitter and they measured things everywhere. And then they changed the frequency and saw what happened. And they saw that things went in 26 log of the frequency. And now we have a lot more measurements, yeah. But initially it was based on very few measurements. And yet we still use those models for most of our designs. So this is what happened when you plot them. You say at a given base station height of, I think I picked 100 feet for that one, or 90 meters, sorry, 30 meters, 2 meter height of the mobile, plot all those models. The COS231 define things in dense urban, urban, suburban, quasi-open, rural, or open. And then the free space is the one we saw at the very beginning. So the free space, remember, has the slope n equal 2. This is the path loss. Earlier it was decreasing because it was the received power divided by transmit power. The path loss is increasing. Yeah, don't be shocked by that. You'll see that all the time. Sometimes it's a path loss. Sometimes it's the received power. What do you notice? Two things. Difference of slope, right? N equal 2 versus the Hata slope, which was, what was the Hata slope? Remember, it was at 44.9 minus 6.5 times the height of the base station. So it's usually 3 to 4, something like that. So it's steeper. On average, those models always have a steeper slope than free space. Makes sense. There's some exceptions. Dense urban corridors where it propagates down. It's almost like a waveguide. It propagates better than free space. The other thing to notice is all those have the same slope, except for the free space. So all the Hata propagation models have the same slope, in dense urban to rural. Does that make sense?
Same base height.
Same base height in the formula. Some criticized that fact and said, you know, it looks like it was just an afterthought. They added those correction terms, but maybe the path loss exponent itself should vary with the morphology, and some other models will do that. But don't be surprised if you plug things and you compare things in rural versus dense urban. It's just an offset. Another one is the COS 231 Wallfish Ikegami. Same thing, that COS project reviewed all those models, put together a great model by Wallfish, Ikegami, Bertoni. They worked on a bunch of things. That approach was different. It was more about a number of consideration around diffraction. They had buildings, and they said, you know, things diffract off rooftops, bounce off the walls, and so they had a whole bunch of different coefficients and parameters, and in the end, by linear regression over many, many measurement campaigns, they came up with that. In a way, it's simpler. And the other thing they said that's not in Hata model is it pays to separate things in line of sight versus non-line of sight. Things happen very differently when you're in line of sight to the base station. In line of sight, they said it's a pretty simple model. 42 plus 26 log D plus 20 log F. At a certain distance, and for below a certain distance of 20 meters, they said, you know, usually it's just like free space. But after that 20 meter, it's that. So it's a two-slope model, if you will, right? There's a little free space sphere, and then something with, instead of a 20 log D, it's a 26 log D, which is pretty similar to, no, never mind. So it's a little worse than free space, which would be 20 log D. And then if you are in non-line of sight, well, that's where things get a little complicated in the Wallfish model. They say, really, there's, again, a distance L0, which is what happens in, say, free space, unobstructed type of environment, plus a bunch of things. A roof to, S is for the street, but the roof to, or screen, sorry, roof to screen, which is where the mobile is. So there's, you know, things come directly, things are diffracted along the roof, and then things go through a multiple diffraction model. And they didn't exactly know how to modelize that. They did with knife edge models, and the justification behind it is somewhat simplistic, sometimes criticized, but it has at least more of a physical justification than the Hata model, which is purely empirical. Unfortunately, you need a number of things to plug into that model, so it's a little more complex to implement than Hata. You need an average building height, right, because things are calculated to diffract off the top of the roofs, so you need to know how high those roofs are. Of course, the height of the mobile base station. And an average street width, which is sometimes tough to get, but still in urban area it's easier to come up with that. An average building separation along those streets, and the orientation with respect to the direct radio path. So all these make sense, right? Because if you're oriented down a road, if you think about the street and the base station is down that street, it's different than if you're at the corner. All those things are very nice, try to make the model better, but practically, how would you do that? You would really implement things there, depending on what you can roughly see, right? If you want a measurement around Denver, you'll go measure the street width and the building, the separation, and, well, you sometimes don't know what to plug in for phi, so you just, you know, say, well, I know the worst case is when I'm 90 degrees from it, so I'll just plug that in. But you can have a best case, worst case scenario. All those parameters are, their goal is to make the model more precise, but practically they make more complicated. Complex, right. It's less general, right? It needs to be more applied. So of course it's easy to be more precise by adding more parameters. If you go back to the ray tracing, if you know the exact configuration of the street, you could have a very precise model, but it'd be a pain to build. So this one tries to be a good balance between just a few general parameters of what happens in town versus just a pure linear regression. And if you look in the class note, you'll see the formulas that depend on all those parameters. They're a little more complicated than Hata, but these days that doesn't really do much. In other words, it's easier to plug in to anything. Let's see. I mentioned earlier the ERSEG model. The ERSEG model was popular for 802.16, which was used for the standard for WiMAX and did things at higher frequency, 2.5 and especially 3.5 in Europe. So they needed something a little higher frequency than Okumura, Hata, even extended. So what did they do? Well, they relied already on a whole bunch of data measured at PCS frequency. So it's kind of interesting, right? The early Okumura curves were at 150 megahertz, and they were used for cellular and PCS. Now that we have tons of PCS data, we're not using it for PCS, but we're using it for, again, higher frequency. It was interesting. But still, they took a lot of data, extensive measurement, and if you read the paper that describe it, a lot of data thanks to the wireless PCS carrier that had lots and lots of cell sites transmitting at 1.9 gigahertz, and so they drove up and down the road and measured a lot of things. And what they measured was interesting in a number of ways. They came up with a model very similar to what was before, right? The path loss is a constant plus path loss exponent times 10 log of the distance plus a normal shadowing of some sort. I don't know why they called the path loss exponent gamma. Usually people call it n, but it doesn't matter. And they used a similar trick that really until a certain distance that they thought was 100 meter, things were very much like in free space. If you recognize that 20 log of 4 pi d0 over lambda, it's this free space propagation, and after that it's this where instead of a path loss exponent of 2 it becomes gamma. And they added they added a variable here which is a zero mean Gaussian random variable in dB, so it really is a log normal shadowing for those who know already next week's lecture. The other interesting thing is gamma, the path loss exponent, has two things. It varies with the height of the base station, just like in the Hata model, right? Gamma decreases when the height of the base station is higher. But there's also, they added a little a quadratic aspect of it. They thought it was not enough to define it as a linear portion of a variation, but that path loss exponent is not quite linear. It needs a C over H. So there's another constant. And they added another random variable to that. So that's not a shadowing. This one is more of a uncertainty or a hint on how spread that estimate of the path loss exponent really is. And so that's a second sigma. The first one well, it's sigma gamma. S itself, not sure how to say that next. All right, so X here represents that Gaussian random variable. And to make this model simpler, they say, well, let's call X, Y, and Z the Gaussian random variable of mean 0 and of standard deviation 1. So that term really is a Gaussian random variable of 0 mean and standard deviation sigma gamma. The other interesting one is S up here is itself a random variable of standard deviation sigma, and sigma itself has a certain mean and a certain standard deviation. So it's kind of funny, sigma, which is already a standard deviation of the shadowing, the log normal shadowing, on average that shadowing is mu sub sigma, but they also give you a standard deviation of how that shadowing changes with a number of things like the type of terrain and the height and a bunch of things, but mostly the type of terrain. So with all that, they started by 4 models, and then they figured that really the 2 middle one could be combined in one, so it was combined in, and the models were whether it was hilly or flat, and the tree density, light or heavy or moderate. And the one in the middle really combined, right, well, let me start with the 2 extreme. When it's hilly and it's got heavy tree density, that's the worst possible terrain, that's category A. On the other end, category C is the best possible things, it's all flat and there's very few trees. And in between, it's either hilly with light tree density or flat with heavy tree density. Well, they said that's more or less the same, so we'll combine that into the model B. What happens? Well, let's look at gamma. Well, I mean, we can look at everything, but there's basically, they give you the parameters for everything, which allows you to calculate, to plug in that simple model, and more than just a 2-slope model, you know, a free space up to a certain distance, and then a gamma slope model. It gives you a little more hint based on the variability and the standard deviation. If you peek ahead at mu sub sigma, that's the average standard deviation of the log normal shadowing. It's going to be 8, 9, or 10 depending on the terrain. And we'll use that a lot for values of the shadowing of 8, 9, or 10 dB. But we also see that the shadowing effect itself varies, and it doesn't vary much in an open environment with few trees. That 8.2 dB of shadowing is fairly constant, but in a very hilly area, that shadowing changes. And if it's hilly, it's kind of funny. In the middle area, I think that changes even more, because I think they've combined more types of models in there. Well, I mean, it starts to be obvious when you look at those numbers, but you really have to plug them in the formulas and play with them, compare them to Hata maybe to understand them well after a while. Very often, at least in the first approximation, you take all those x, y, z to be 0, right? You just ignore any variation, you just plug in there the constant value for the path loss exponent, and that's all you need for the model. The rest is just icing on the cake, if you will, to give you more details. Any question on the Ursig model? Yep.
Is population of the area under consideration ever considered? Because
not in that model, no.
none of the models?
In other models.
Because you can, I mean, the signal can behave differently if there is
Right.
a lot of population in the same area.
No, it's usually not.
I think it's only considered when there are huge gatherings or something like that.
Well, I mean, the Hata model has a dense urban versus rural. That does take an average, presence of people there. It's an excellent question for higher frequency. 802.11ad and Y gig at 60 gigahertz is very concerned about that. A room full of people is a very different environment than an empty room at 60 gigahertz. And that starts to be well understood indoor, but think about now the 5G outdoor and what we talked about all those frequencies above that. It's not well understood. So there's certainly room for research and improvement in an outdoor model considering people and other things in the way, more than just trees. That, to answer a question, how do we come up with those models? This is what usually happens. People make measurements and then do a couple of things. Compare them to existing models or just do a linear regression and come up with their own models. It's simple, right? If you measure, this is a number of things I measured at 5.8 gigahertz long ago, and we flag differently the ones measured in line of sight versus non-line of sight. And then in this case, I could have just come up with my own model, or I decided here to compare it to the Hata model in urban, suburban, rural, open. And what do you see? Well, it looks like the suburban model. This was all measured suburban. The suburban model works pretty well with the non-line of sight in the suburban model, which makes sense, right? That's what Hata measured. And when it was in line of sight, it seems to work with a rural open, which is odd because it was not rural open. But it makes sense that it's in the line of sight. It just would act very similar as in a rural open where there is a line of sight. I measured that at 5 gigahertz and I compared it. Remember that the Hata model should not be applied at 5 gigahertz, which is why you have to be careful. This was measured in suburban areas, and I just had to be very careful because if you average all those points, it does not seem to fit very well the suburban model of Hata, right? It fits well the non-line of sight measurements, but not the line of sight. So be careful when you extend to different areas, either in distances, in frequencies, in other things that don't really fit the model. Be cautious about it, and you may have to add some restrictions of this or that. Anyway, just an example. And as I said, rather than just, and that's really, I was talking about these sets of measurements here at 5.8. You know, if you measured the line of sight one, it was about n equal 2. If you measured the non-line of sight, it was 3.5. So I could have, you know, that's 3.5. That slope was n equal 2. That's my own model there. So basically, that's what people do. At least in the 90s and in the 2000s, they did that a lot. And now I think they're doing it again at 3.5 gigahertz and maybe at 60, 80 gigahertz. There's a lot of other renewed interest. Why renewed interest? One, new frequencies at 3.5. Two, 5G considering millimeter wave. It's starting to be well known indoor, but outdoor, nobody knows. Well, I shouldn't say that. There was some LMDS. We know some line of sight. We know a number of things, but not to that extent that we would like to know. So great opportunity of research for you guys. Go out there, measure everything, and whenever you see something that correlates, that looks interesting, write a paper on it. And maybe you'll be famous and you'll have your name there next year, in the next class. And what do all those people do? Very simple things. Measurement campaign at a given frequency, usually, in a given area, and they publish it. So what I did here is just go look at all those things and compare them. And what do you see when you compare all those things? I've compared a lot of things, from fairly low frequencies to fairly high well, I shouldn't say fairly high. These days it's still low, but from less than a gigahertz to 6 gigahertz almost. And I've started notice. So for each one, I looked at the path loss exponent that they reported, as well as sigma, the standard deviation in dB of the log normal shadowing, which we'll talk about later. And I've seen that things seem to be sort of consistent, and I shouldn't even have separated them, right? Because there's not that much difference between 3.0 and 3.1. So on average, if you do all those, the path loss exponent seems to be around 3. And the shadowing, the log normal shadowing, seems to be 8.7 to 9. Remember, pretty similar to the ERSEG model. It's good to see, though, that's one good thing. If you don't know what to do, just use a path loss exponent of 3 and then log normal shadowing of 9. Because it fits a lot of measurements. I tried to see a bit of a variation in frequency here. The shadowing seems to change with the frequency. So at 1 gigahertz it was 9, but if you go below that or above that, it changes a bit. It is good to see, though, that some of them changes a lot. I mean, some are as low as 6 and as high as 10. Same for the path loss exponent. Some are as low as 2 and as high as 4. Usually depends on how much open versus dense area they measure. But again, if you go do that at 3.7, especially 3.5. Do it, look at the various variations between line of sight, non-line of sight, look at the shadowing, look at any other aspect. Everything that we'll see this week and next week regarding small scale fading effects and parameters and large scale effects is something very interesting to go measure these days. I'll take a break really shortly. I just want to mention multiple slope model. We've seen a couple of already two slope model, right? Because very often they say things happen in free space at a certain distance of the antenna. How far from the antenna is up for debate. Some say, 10 meters, 100 meters. For millimeter wave, Rappaport in his book suggests 1 meter, because at millimeter wave, at 1 meter you're in the far field, things are already well explained, and things can start to be obstructed. And then at some point they said, why only stop here? We can have 3, 4, 5, 6 slopes. And more models came out and did, including ERSEG in a paper, proposed some extension to more slopes, but really they have very little benefit. I mean, if you look at the uncertainty, adding more slope doesn't seem to fit much better, and as a result they were not too successful. They do have improvements, and they're not that complicated, so I'm not sure why they were not too successful, but still, that's what happened. I think we may see again more of them indoors, especially at millimeter wave. Maybe that multiple slope would become more important. A quick word on indoor model. I'm not going to talk much about that one. That's such an obvious one, really. When you don't know what to do, you just assume it's a constant plus, that constant that, that depends on D0. Let's say it's just free space model plus an attenuation per wall you go through plus an attenuation per floor you go through. And the wall and floor attenuation in this simplistic model vary with type of material, thickness, etc. And we'll talk about that later, but that's pretty simple. Let's talk about a couple more things, and then we'll take a break. We've seen in most models a variation in 20 log of the frequency, right? Wallfish, remember, was 26 log of the frequency and has been criticized for that. They said, theoretically, there's really no reason why it should be any different than 20 log of the frequency. So you should fit all the other parameters to fit a 20 log frequency in your model. Right or wrong, if your measurement campaign seems to show something different, why not reflect it in the model? But then all those models struggle with what to do with different obstacles, trees, buildings, etc. Building penetration is especially difficult. Foliage is difficult. It changes with seasons, with the type of trees, and many papers try to find some model. Some looked at the size of the leaves and looked at them at little ellipses all around the trees. I mean, there are some wonderful models, and a number can be used and are very often used by software in the industry in a couple of ways. They either do a single tree model, and then you try to estimate how many trees are in your path, and you remove that from or add that to your path loss. And then others just do a loss per meter of vegetation in forest, etc., and then you try to estimate. Think about software propagation models like ATOL, EDX that we'll look at later. You have map of morphologies, right? Some tells you this is a forest, this is a street, this is a forest again, and you can add loss per meter of forest in a ray tracing analysis. So that's usually how they impact it. And you can find a little more in the class note. This is a summary of what I've seen, either in loss per meter or in a single tree model, depending on the frequency. And some loss are pretty high. I mean, those are pretty high frequency. But a single tree can be at modern microwave mobile frequencies, and the 2-3 gigahertz can be a significant loss of 10-12 dB. And the loss per meter along a path are usually smaller, but of course in the forest it adds up. Things change with leaves or without leaves in the winter. And oddly enough, some papers and some measurements I've made show that things change before the leaves come out. Right? It seems obvious when a tree has no leaf, it has less loss than a tree with leaves. But it's funny because we started measuring loss a week before the leaves came out. So maybe there's a sap, more liquid, which is lossy in the tree, and we did notice loss, and then leaves came out. So sometimes we do find some interesting results. Another very interesting foliage model I recently found in an interesting handbook here on chapter 4, and it is available online at the library here. If you search that at libraries.colorado.edu, I think you can see the book online. I don't think they have it in the stacks, but they have it online. And that model says that why should the loss be per meter of forest, right? There's no fundamental reason why there's not a different exponent here on the distance through the forest. And so some of those models try to calculate the path loss exponent through, it's an exponent. But instead of a certain loss per meter of forest, it turns out it's usually more of a loss per square distance of the forest, square root, right? A lot of those are around 0.5, even even less. So, interesting models, very different models, but this one I thought was a very interesting comparison. Things are not always easy in a forest. Things vary with the frequency and with the distance in the forest, but not necessarily linearly. And let's take a 10-minute break. And unless there are any questions in foliage, and before we get to, when we can go even to building frequency variation. Let's take a break. And be back in 10 minutes, please. All right, let's get started again on foliage. Any other question on that? So I just found this reference, that Handbook of Position Location. It's a very interesting book, so it's not referenced yet in the class notes. If you look for it, search for that, copy paste that in the library search, and you'll find something. The other interesting aspect of that table, the chapter 4 is a very interesting analysis of what happens in different situations, including at the end foliage. But the interesting aspect here is, and all the references are in the book, but compared to what we've seen earlier, all the models we've seen stop at 2-3 gigahertz. These models have been done on a much wider area of research regarding frequencies, and they do extend from less than a gigahertz to 95 gigahertz in some cases, certainly to 6 gigahertz or 20 gigahertz here. So those are very interesting if you start looking at more, those latest 5G bands of spectrum, and if you're trying to see what's happening there. One area that's not well known, as I mentioned, is what's happening outdoor. So I'd encourage you to look at that, research that more, because that will be very interesting and is really an area of focus of the industry for how to use those new bands of spectrum for 5G. Mostly, they will focus on using that for indoor models, so foliage may not be the most important aspect, but still, think about a way to distribute high-speed wireless data to suburban area with everybody, has a tree or two in the front yard, it is important to know how to model that. So I'm starting to try to gather things that most people in the industry have ignored before, that were, not really relevant, things for LMDS at 28 gigahertz, etc., that are now much more relevant for mobile communications. So start looking for things, and all those references, so those numbers, 34, 40, 41, 42, are references. I just copied that table from that reference. So those are not my class note reference, but they're really from this reference, the Handbook of Position Location. Right? So don't look in the class notes for in the reference in the end. Don't try to look those up. Those are really from this book, the Handbook of Position Location, which is a great book on positioning location if you're interested too. Finally, one of the most difficult things to predict is how well the signal will go from an outdoor environment into a home. That in-building penetration. There's a number of reasons for that. The main reason is that the outdoor environment is very different from the indoor environment. So you're really trying to measure something fairly complicated. One easy way to measure it would be to put a horn on the outside of the wall, right, and another horn on the inside, and measure what happens, how much of the energy is absorbed by that wall. And we can do that, and that gives you part of the answer, but not all of it. It turns out that things depend on a lot of things, including the angle of incidence. And so if you just measure things with a horn, you can then change the angle of those horns, measure things, or you can come up with models, and we'll see that in a moment. The other thing is things depend on frequency. Once again, I've done a number of measurements here. Those are not from the from various sources, but things I've done through very simple measurement campaign, and you see things vary with frequency. But the picture is actually more complex. That's saying, on average, at 700 megahertz, right, a residential building will have about 6 dB attenuation. On average, at 5.8 gigahertz, a residential building will have an 18 dB attenuation. True, this is what those measurements show, but if you really want to penetrate 90% of the buildings, or 90+%, you see that this becomes very steep, especially above 90%. It's just very difficult to go reliably through every building, unless you have an added margin of 30, 35, 40 dB, which is, which you can't afford. That really shrinks your cells, etc. So it's very difficult to predict how well the signal will penetrate in buildings. Now, this is all things being equal. I'm not looking at various angle of incidence, etc., because it sometimes is nice to have a model that just gives you an arbitrary value. If I had to take an arbitrary value, I'd look at that and I'd say, all right, I've got a propagation model, right? I can use Hata or something like that. It'll tell me if I have a base station that's 90 feet in this suburban area, it'll tell me my coverage. That's fine if I want to put a device on everybody's home. But what if I just want to ship them a little modem that they'll put on their home? How is that going to go in their home? Well, it depends on a lot of things. If you put that, let's say I have a system at 700 megahertz, so I assume it's going to be about 6 dB. The median value to penetrate is about 6 dB. If I assume that, if I put that in my link budget, that means I can get about 50% of my customers. Is that good enough? Well, probably not. I probably need to reach at least 90% of the people in the area, right? So I really should use at least 10 dB in the link budget. If I really want to get more, if I want to reach absolutely every home, I should really use 20 dB in the link budget. So that can be very difficult. That also is just a first wall penetration. If you're in the home, you know, in the kitchen, by the window that's facing the base station, it's one thing. But can you assume that the customer knows where the base station is, know that he has to put that modem near that window? Maybe you can tell him, you know, because you know where the base station are, so when they order service, you can say, you need to face this on your south wall or something like that. But if you want throughout the home, it's another thing. So you'll see first wall penetration, second wall penetration, etc., and usually it adds back to the Motley Keenan model, right? You have to add dBs of penetration for every time you get through a wall. Not easy. Well, we get to the next one. So I looked at, again, what was published in the area, and I split it in two, residential versus urban, because residential area are quite different from dense urban core, right? Those high-rises are very different from residences. And here's what I found. So let's look at the residential model on the left first. What do you see? A general trend seems to increase with frequency, right? The lower the frequency, the better it penetrates in the home. Why is that? I mean, if you don't know, it said because that's what people published, right? Measurements show it. Yes. Is there an intuitive reason why lower frequency penetrates better? Freeze? Good guess, but this removes the propagation parameters. This is just the dB loss of what it takes to go from outside to inside. But you're right, Freeze equation says that at a higher frequency, you do still have to go through a certain distance to go through there, and therefore, yeah, there's more loss there. Higher frequency. Yes, there's that common conception that an object is almost invisible if it's a smaller size as the signal's wavelength. In other words, a signal of, you know, hundreds of meters of wavelength would not even be seeing any obstacle like a wall like us, but a smaller wavelength sees more obstacle, is more attenuated. And that's a general aspect, yes. The higher the frequency, the smaller the wavelength, the more it's attenuated by little devices, particles, obstacles, scattered, etc., that waste power. So these are mostly median values, and you see that if they're fairly reasonable below 1 gigahertz, they start to be pretty high after 2 gigahertz. The other thing is that the lines report the same type of papers measurements. So if you look at the Aguirre paper, it's that blue line. If you look at the Wells paper, it's that blue line. If you look at my personal measurements, that gray line. That shows you quite a bit of difference, right? If say at 2 gigahertz, these people seem to think it's about 7 dB of loss. Sergio Aguirre said it was about 8 dB. This guy and my measurement said about 12 dB. What's the big difference between those? And that's really the point I was trying to make earlier. How you measure that in-building penetration. The method that you use has a huge impact on the measurement results. So if you go measure that and publish any result on that, you have to be very detailed on how you measured it. You can't just say, measurement throughout the city of Denver show, blah. You have to say, I measured this with a horn facing, 90 degree on every wall, and I measured that. Or, on average, I put a base station here and measured throughout down the street of about 100 meters, every home on average with an increasing angle of incidence, and my result is this. The point is, it's very difficult to compare apples to apples in those papers.
Well, but by way of comparison, though, on the residential side, you're seeing only a variation of 5, maybe 6 dB, whereas on the urban, you're seeing variations of 20 to 25 dB in these various...
Yes, I was not even getting there. I was just looking at residential. Okay. And
right.
Look at residential. Between 1 and 6 gigahertz, things moved from 6 to 12 dB. But between one paper and another, things moved from 4 dB. So the uncertainty there is around 4 dB, and the value you measure is around 6 dB. So it's notoriously difficult to measure in-building penetration, and your method of measurement has a big impact on your results. So big, in fact, that it's a good percentage of your result. Now, that's for residential. Now, if you look at urban building, you're right. First of all, it's all over the board. Again, especially these guys measured something crazy there at 25 dB high. Everybody else seems to believe it's between, 5 and 20 dB. But again, between 5 and 20, that's a big difference, right?
Between 5 and 20 is a lot bigger than between 6 and 12. I mean, that's the...
Well, yes. But that's almost embarrassing. It's like if I ask you a question and you say, removing dB, it's between, a factor 10 and a factor 200. It's basically saying we have no clue how it attenuates. The other interesting thing is to see what happens when the frequency increases. Some of these papers say the frequency increases a little bit. Some of the papers say the frequency is pretty much fixed until a certain critical frequency, then it jumps up. Another paper says it actually decreases with frequency. And another one says it doesn't change at all with frequency. So, once again, how many opinions can you have? Well,
see the green one.
So
it's just a straight line.
Basically, nobody knows.
So is this going to be on the test to be the next logical question, right?
That's right. You can't be wrong on that one.
The green one is funny. It's just a straight line.
The green one is great. He was very proud of saying there is with the right set of measurement and the proper method, there is no variation in frequency. Another one, Turkmani, who has published some great papers, said it actually decreases because if you measure things well, there's always large windows in urban buildings that have a bigger aperture, and then smaller wavelengths penetrate that easier. And remember the auctions, the 700 megahertz auction versus the AWS auctions? A lot more people spend on 700 megahertz. And then the guys who spend money on the AWS auction cited that paper to saying, our spectrum is great in urban building penetration. Right? Look at those poor saps who spend money on 700 megahertz. It doesn't do as well. We're happy because AWS goes great. And yeah, that orange guy there, tennis, proved the same. It actually, there's a decrease. And again, if you look at the details, in some cases, a large window is many more wavelengths to enter at higher frequency. It helps. So you have to be careful what you measure. What else? Any other comment on those? The point is you have to read the paper carefully when you compare it. The main reason is what I mentioned earlier. Things vary greatly with the angle of incidence into the building. And even more than that, things vary greatly with the morphology, environment, or whatever happens outdoors. Think about it. Depending how many multipaths you have hitting that building, things will be very different, right? If you have only that one ray that comes at an oblique angle, it may not penetrate very well. But even when you think you have a system with just that one ray coming at an angle theta 0, what may happen is you have a multi-path environment and you have many other rays that penetrate, say, almost perpendicular, and it's not at all the direct ray that penetrates better, but it was another one that bounced off several buildings and came perpendicular to go in better. So that's why it's very difficult. The other thing is things are very multipath rich indoors. So when you think you're measuring just an in-building propagation, really what you're measuring on the indoor is something that might have bounced through other windows, come in through other ways, and so anyway, it's very difficult. And and as a result, the results are all
Where's
over
the
the
easy
board.
part?
Yes, the easy part is that it doesn't really matter, right? You just want to know how good the signal is inside. It doesn't matter how it comes in, but the point is it's not very repeatable. You can have, say, an identical building built exactly the same and measure very different in-building loss depending on the neighbors of that building. So whatever model you come up with, should probably also include what's around the building. Are there trees? Are there other buildings nearby? Etc., etc. Especially, again, I'm probably sounding like a broken record, but again, as you start going to the 5G and you start building your expertise in propagation modeling at higher frequency, keep in mind what's around. Because I'm sure your boss will ask you, well, it's all very well, but what if I bid on that 28 gigahertz block now that the FCC is auctioning, but how well is it going to penetrate into homes? And you could just go out there, measure, and say, well, it'll be about 28 dB. Or you can say, be careful. We've learned that it depends on what's around, so it depends on how many trees, it depends. And at the end, he'll still say, yeah, I don't care, give me a value, and you'll tell him 28 dB. But at least, you know what I mean. You need to understand all the parameters. One interesting indoor propagation model is, again, COST 231. And again, Chapter 4 goes around many of those reasons why it is difficult to go through that. I encourage you to read it. And they come up with that model, which you may recognize the constant from, what is that, the free space model, plus 20 log of something weird there, S plus D plus, of course, the propagation indoor. And where did I put S plus D? Well, it's the outdoor portion of the path plus the indoor portion of the path. And then COST 231 said, well, indoor things happen differently if you go through many cubicles or rooms versus down a corridor. So depending on the areas, if you think about a heat map on those things would be different in this corridor, that D prime, versus going through many walls. And so the indoor propagation is different. Plus, there's a term here which is really what we're interested in, that L indoor, which is the loss that it takes to go from just outside that wall to just inside that wall. And the model is interesting and says, that indoor is really depends on a number of things. It depends on the material, so we'll have one constant L sub E there, which is The loss when you really hit that wall with a 90-degree incidence, so straight on. That's that loss. But there's also an impact, and they explain why it's really impacted by the angle theta as 1 minus sine theta squared. So there's that LE plus a term depending on the incidence. And that one is very difficult to measure, but it's around 20 dB for urban concrete with windows type of building, and about 10 dB for residential, wood sidings, etc. When you don't really know, or you want an average on that, you can just take a average for a wide range of angles, and there you go. It's about if you remove that, instead of that LGE, this is a little confusing, but instead of that second term, really you're replacing all that by just this one, that L prime. Independent, if you don't know really what, and on average you want to say there's some kind of statistical distribution of incidence that I don't really know. If you do know it, right, if you do study a specific area down the road, you do use that theta. If you don't know, you just can do an average, which is another 4 to 6 dB. Does that make sense? So it's back to, Doug, to your question, a site-specific model is interesting, but is less general by design, whereas a very general model is good as a first approximation, but it's not accurate enough in many cases. And those COS231 model try to be a good balance between the two. And then, if you look at the detail, that max of gamma 1, gamma 2 is whatever it takes, whatever indoor you measure, you also have to add that. So after the indoor penetration estimate, what happens indoor is usually very site-specific. You can say on average, I've seen model, let's say on average for a home of so many square feet, you should account for so many loss. Practically though, when you try to cover Wi-Fi over a suite of offices, etc., you do a site-specific model and you put every cubicle, every office, every window, you run it through the software and you see what happens. You do that because it's not like collecting terrain data over a wide area. It's something that you know and you have access to, and so very often those are site-specific. Site-specific models, of course, also exist for outdoor, but then you just need to have terrain data, building data, and even morphology data, which is, is it a field, a road, type of a lake, or a built structure. And we'll try to do more with that with EDX later in the semester. So all these models we've seen are in a way fairly simplistic, right? They measure the power as a function of distance. You have one transmitter, one receiver, and there's distance, a path loss exponent, tries to get rid of all the other shadowing, small scale fading, all the stuff we'll see next week, I sort of averaged out. That's all very well and good in a first approximation, But in many cases, it's not good enough, especially if you think about MIMO and other things. But it is important to have more than just a one-ray simplistic model when you deal with more complex systems such as MIMO. Why? Because you really want to estimate the rank of that environment. You probably don't know what the rank of a MIMO setup is. We'll talk about all that. But in some cases, the same transmit system and receive system will have a great MIMO performance in one environment and a very poor MIMO performance in another environment. It depends on the amount of multipath, and that's the rank of the system. How do you predict that? It's very difficult to predict, so you need a number of other parameters, terms, and we'll look at all those parameters next week. We'll try to simplify them, but basically we know that it's not enough to say there's a transmitter and a receiver at a certain distance. We need to know a number of other parameters. Do you know what those parameters might be?
Delay spread.
Delay spread, very good. What else?
Coherence bandwidth.
Delay spread is what? Is an indication of
Coherence
the
bandwidth.
multipath, yes, coherence. There's going to be a number of parameters that we'll see next week that tells you about how multipath rich it is and how fast things change. Mostly it's the delay spread and the coherence time, coherence bandwidth, and that's related to delay spread, Doppler. All those factors, we'll try to use them. And that's what those models use. Well, there is the root mean square delay spread. And it turns out that with different delay spread, you can model several environments. It's may not be enough, and we'll see why. But still, those are called dispersive models, and they're used in various environments to reflect not only the general power distribution of your model, but how multiple rays can be used to reconstruct in a type of equalizer, in a MIMO system, etc., versus just a one path loss model. And I didn't go in too many details. There's a great paper on TGN for 802.11n and AC, and you've probably seen more of it in 5520, where they basically say there's packets arriving. There's an exponential distribution of them. They arrive from different directions, and with that, the model can be used to explain different things. Those dispersive models are very popular for LAN, wireless LAN, but are not really used in the wireless industry. So instead, we still rely on those old Hata model and so on, and we do something a little special to try to estimate the rank for a MIMO system for the capacity, because that's really all we care about is the capacity of the MIMO system. And then, so we use the old model, add something that we'll see when we see MIMO, and that's about it. There's my broken record again. Focus on all this for millimeter wave and 5G. That's really the area of interest in the next couple of years. And a lot of work is required on millimeter wave. And not just measuring things. The indoor channel has been studied fairly well, mostly for 802.11ad and WiGig, and that starts to be understood. But the outdoor channel needs a lot of good ideas. Right? The normal approach is to measure things and do a linear regression and try to measure the slope and so on. But we need maybe a little better than that. We need to start identifying the important parameters for that propagation modeling. Maybe it's more the angle, the beam width of the antenna, the angle of arrival distribution, maybe the height, the orientation. I mean, there's many things that should be really studied. And I think they're not quite known yet. But at some point, someone will come up with the right set of parameters and say, you know what, given these parameters, things behave that way at millimeter wave outdoor. Those parameters may involve what we've seen so far, what we'll see next week in terms of treating the amount of multipath, of Doppler effect, of coherence in the channel, but they may involve many other things that we haven't quite pinpointed. That's your job, to find the best way to do that well. And those channel modeling will have a lot to do with time and frequency correlation, with a bunch of other aspects that we don't understand well outdoors yet. Especially if you have time, read chapter 3 of that new book by Rappaport on millimeter wave wireless communications. It goes over a number of papers that have already published things on that and the limitation and what needs to be researched further. Very interesting. And I can give you a little more when we study microwave, millimeter wave paths in a couple of weeks. I'll tell you a few more things about what will apply and what should be done, what might be interesting in that area. Any question on that? Otherwise, start thinking about what you can do. Buy a cheap 802.11ad access point, or if you want to do a project or a capstone or something like that, think along those lines of what to do in millimeter wave and 5G propagation. Not indoors, though. People know that. But take an 11AD and put it outdoors and see what it happens down the street. Or, they cost $300, or we can buy one and you can have it for a test, and it'll be very interesting. That's it for today. Homework 3. Let's spend a little bit of time looking at homework 3 before I go back to homework 2. Any questions? So homework 3, number 3, 4, and 5. Let's see. Not sure how I can center this. Maybe I need to stop the presentation. All right, that's better. I didn't talk about in-vehicle loss. It's similar. There are some similar things. What did I say? 3, 4, 5. So, yeah, let's move to 5. Let's start at the beginning. So, this really focuses on number 3, plotting path loss prediction versus distance. Really focuses on the early models. So just plot something very simply using the 3 models: free space, COS231 Hata, and ERSEG. As I told you, if you don't have to deal with uncertainty, so just use x equal y equals 0 in the ERSEG model. In other words, all the standard deviation are zeros. Everything will be fixed. But compare what happens at a certain frequencies with certain heights of base station. How do those models compare? We've seen already how the free space model compares, right? It'll be a little too optimistic versus the others. And then what's the cell radius at a given distance, and repeat the problem at a different frequency. Now, number 5 is the one that will take a little longer. I don't know if you can read it. Ooh, now I can read it. Where you really need to recreate the graphs that I showed you. Basically do a quick free space model and compare it to the 2-ray model. But to build the 2-ray model, you need to have to write a program. It used to be very hard to get access to MATLAB. Hopefully you can have it. If not, if you have a Mac, Python could do it. I mean, there's lots of ways to get to it. I just want to make sure you all have a way to do it. Does that seem fair? And you see, the equation are very simply in the notes. It's just a matter of implementing the right thing and finding the right sampling for the fades to look good and the right software to plot things in log normal, and you may have to try and error a little bit, but start early, have the questions ready for the TA early on. She told me that she had a lot of questions coming up at 11 p.m. on Monday night. Please, you can't expect people to be listening. Although I was there, I was online trying to make sure, and I was very worried when I saw nobody submitting anything before. I think only at 10:30, only 4 of you had submitted, which is not bad, 40%. But try to look at it earlier. Ask questions early on. She has her office hours Thursdays. My office hours are too late on Tuesdays, but send us email if you have to. But it's like doing any job at work. Don't expect people to be up at 11 p.m. when you need them in a rush. They need time to look, read, and answer. Also, one of you submitted 2 minutes late, and I send him a nastygram. I'll have to reiterate the lesson. It will happen, but the easy way to avoid that is give yourself a margin of safety. Don't plan on submitting things at 11:59. Something will happen one day. You will not do it on time. Why don't you make sure you submit it at 10 or 11? That's still plenty of time. In case something happens, you can do it later. It seems obvious, but do it, because if you do submit it late, you will lose credit. And keep that in mind when you have a customer that needs something at a certain time. It's not okay to have an excuse and say, I was only 2 minutes late. When you want a grant from the federal government, you need to submit things on time. When you have a customer presentation and you're not there on time, you've lost it. You can try to convince them all you want that you did a better job than a competitor. You've lost them. So please focus on deadlines. It's very important. Any questions on homework 3? First 2 should be fairly quick, implementing the model. The third one will take a little longer. Yes, question?
For the first 2 problems, are we supposed to submit the code?
Yes, for all of them, submit the code in whatever you do, and do a little write-up with at least plot the picture and the answer. Yes, but do submit the code. It's not too long, shouldn't be pages and pages. We do have a couple of minutes. Were there any questions on homework number 2? Or
Third one.
what's that?
The third question.
Third one? Third one. What was that? I'm not sure if I can find it. Third. That one? The capacity of a voice per channel? That should be fairly straightforward. Did I change? Do I not have the right? Did you mean the second one?
No, the third one.
The third one.
Yeah.
Okay, what's the question?
I'm not sure what kind of formula goes for voice channel per cell per megahertz, since it's a GSM system.
Right, that's why I gave you the answer. You couldn't get to the answer? So could you get to the answer of A?
Yes.
Right, the amps, you cut the amount of spectrum you have, you know that each one uses a certain channel width given by the amps standard of 30 kilohertz, and so you get how many calls per megahertz per cell. What happened in GSM? What's the channel width in GSM?
200 kilohertz.
200 kilohertz, and what's the time slot?
8 time slots. 8 time slots. 7 is the cell count. 7 is the cell count.
7, right.
It's 8 over 7 over 200 kilohertz.
8 and on. What do you mean 8 by 7?
So it's channels per cells per megahertz, right? So
right.
8 channels and 7 cells and 200 kilohertz.
Oh, reuse factor, right. There's a reuse factor of 7, but you have 8 time slot in that 200 kilohertz, and if you do that, you should get to 5.7, right? You had to figure out a couple of things, but they were all in a class note somewhere, right? So the reuse of 7, divides the capacity by 7, which is unfortunate, but the 8 time slot multiply the capacity by 8. So you have 8.
For AMPS, how many time slots are there?
1.
Just one?
Yes. 1 time slot, but in 30 kilohertz channel. So here in amps, in GSM, you had many, many more time slot, well, 8 times more. But still, it's not much higher because the channel was wider, was 200 kilohertz instead of 30. So GSM was not really a big capacity gain because of the wider channel. Okay. Not too many concerns on taking the limits with different things being fixed. It's just a little mathematical exercise, right? Some things are fixed, others are...
Depends on what
Things we take as constants.
Yes.
So
You had to fix some things and vary something else, take it to the limit, and A and C were fairly obvious, I think, but B might be a little more... it's not always... It's not infinity when W goes to infinity. The capacity doesn't necessarily go infinity if you have a limited amount of power. So, all right. Well, if that's so. Again, get to it early this time. Let me know if you need me to be on campus on. Maybe next Monday. I'll be on campus next Monday, but try to get to it before next Monday. So, thanks.
Professor Schwengler, this is Doug.